Cool. Last time we talked about radial basis functions and in general non-parametric regression models. And I have to do a hard start today without the beautiful selection, like the beautiful intro slides, because I didn't have time to redo the slide decks. But anyway, what I left off, and I wanted to leave off entirely, but then I realized actually I need to talk about it. So this is the end of the lecture that I didn't cover last time, is basically an alternative approach, an alternative gradient-based approach for model selection, which is really important. And then we'll move on to today's lecture. So previously in the course, we talked about search and score for feature selection, where we like to find some sort of score function and then search for features with the best score. And we basically did this using the L0 norm, or talked about doing with the L0 norm, where you explicitly basically count, this basically counts the number of non-zero entries in our parameter vector, right? And we explicitly try to penalize based on that count, simultaneously minimizing the loss. And this, and you know, different things happen with different strengths of regularization. You know the story, right? The issue is that it's hard to find W with this with this objective, right? It's not differentiable, not smooth, all that sort of stuff. So what we said is we talked about forward selection, where we search for the best one variable model, and then consider all other features and search for the best two feature model, and then search for the best third feature to add on to that, so on and so forth. And this, of course, requires a squared number of operations in the model fittings actually in the dimension of the parameter space, right? That's gross, right? So that's not good, right? So what if we want to pick amongst millions or billions of variables, which will happen when we have very, very large, non-parametric models where n gets big, or when we have just a very, very large number of features that we make up for whatever reason, right? So if D is large, then doing forward selection based on what we just learned, if we have to fit a quadratic in the number of features, number of models, and for instance, for least squares linear regression models, we know that's the cost of actually fitting the model, then the total cost starts to run as D to the fifth. And if we have a large number of, we should really call these features, right? If we have a large number of features, we're really, really totally hosed here, right? I mean, we're already had problems here, so we're talking about gradient descent, but if we're doing model selection, it's bad, right? And if we're not doing, basically squares, right? For robust regression, we need to run gradient descent OD squared times, right? So, maybe that's, ONDT or whatever, but this is actually, in reality, this changes, the linear factor in T is really bad for gradient descent, right? And with regularization, we need to search for lambda this number of times, so on and so forth. It's really like, you can't do search and score, really, if you have a large number of features, like over 1,000, something like that. So, and we're going to go through this really quickly because we have a bunch of other stuff to do today. But the basic idea is instead of using the L0 norm here, so we can have the L0 norm or we don't have to have the square here if we don't want to, or the 2 norm. Let's think about actually regularizing by the L1 norm. Okay, so what does this do? Like the L2 norm, it's convex and improves our test error. In other words, this norm on W is going to attempt to make the absolute value of the parameters small, right? And like the L0 norm, although this is not super obvious, we'll try to get to it, it's that the L1 norm actually encourages weights to be exactly 0. Okay, and a lot of that actually can be seen by looking at basically the difference between these two losses, this being the 2 norm and this being the 1 norm. When we're considering what's happening in gradient descent, and we're basically summing up a whole lot of these kinds of functions, but we think about one parameter and one data point is what this is, what this plot is right here. The gradient signal that we get here, and we'll talk about this in just a second, and the gradient signal that we get here are very, very different. Okay, that's really what causes this to happen. So L1 regularization simultaneously regularizes, makes the individual elements of the parameter vector small in absolute value, and selects features. In other words, actually drives some of them, in fact, a very large number of them, an exponential number of them, to 0. So it's super fast in comparison to search and score, because you can do gradient-based learning in models with L1 regularization. And this particular form of model right here is called lasso, or this form of regularization really is called lasso, or the lasso. Okay. You're familiar with the regularization path plots at this point. So here we have a linear regression model again with L2 regularization on the left-hand side. And these are the weights assigned to a number of features. And the critical things that you should recognize is, or remember, is that as the regularization strength increases, the absolute magnitude of all of the parameters gets closer to 0, right? As you increase the regularization strength. But you should notice that actually none of them equal 0. They get very close, but they don't actually equal 0. L1 regularization, this is, oops, on the other hand, looks like this, where here regularization strength is along this axis. These are the parameters again, but you'll notice that actually these regularization paths result in various parameters being actually equal to 0. Okay, and this is a little bit subtle, and we have to go through it really quickly. But so here is a loss and a particular parameter value, and this marks the minimum with no regularization. So W star is here, right? If you apply L0 regularization, right, you compute the loss with you have the standard loss, but it has a discontinuity and a jump down to some other loss if you set W exactly equal to 0, right? So there's some baseline loss, and in fact, you would choose this to be the minimum, not this to be the minimum in the case of L0 regularization, right? So you would say, okay, let's just not use this particular feature because it produces the lowest loss, right? L2 regularization takes the same curve. So this curve is exactly the same shape as this curve. It doesn't move anywhere. It just has this kink at 0, where you evaluate the model with literally, the weight 0, right? L2 regularization just shifts the minimum. So this is the minimum here, closer to 0, right? Because it explicitly encourages small parameter values. L1 regularization arises from actually adding up 2 different losses, one the data loss, right, and the other the regularization loss. And depending on how those 2 are situated, usually there will be either it will look something like this, or it will look something like this. That was terrible. There should be a line over here, and basically the point is there's a kink at 0. Okay, all right. And quite often that kink, because of the characteristics of adding these two losses together, quite often that kink actually produces a minimum value directly at 0. Okay, so if you're using gradient descent techniques, you're going to go to here. If you're using gradient descent techniques, you're going to go to here, but you have to evaluate all of these 0 points, right? If you're using gradient descent techniques, you're going to go to here. But the gradient signal very close to the origin in these 2, where you actually can use gradients. This you really can't. You have to do gradients plus some sort of combinatorial thing, right? The gradient that you get for learning W, the learning signal that you have is very, very small, right? And over here, the gradient is large all the way to 0, basically. So you always have big gradient signal. So, L1 regularization gets sparsity, but L2 regularization doesn't. What's the deal? Don't they both shrink variables towards zero? And what I just gave you is kind of the fundamental intuition, right? So if you're using L2 regularization and you have some parameter that's small, the penalty in an L2 sense is something like that squared. So it's really, really small. So there's very little incentive or gradient signal in terms of decreasing the loss to set it to zero. And critically, as you get closer to zero, the incentive decreases further. Like the loss term that you're trying to learn from gets smaller because of the squared thing. And that's exactly because it smooths in the function. The slope goes to zero smoothly. The slope derivative is actually the incentive to move closer to zero. With a non-smooth function like L1, on the other hand, the slope stays constant the whole time. It doesn't diminish to zero. And even when the weight is really tiny, i.e. very, very close to zero, there's still something to be gained by making it even tinier all the way until you're exactly at zero. Okay. Great. So L2 regularization, since there's changes in the data, it decreases variance, i.e. basically it leads to lower test error because of the arguments that we made last time. There's a closed form solution. That's cool. The solution is unique. L1 regularization has the same two first properties, but it requires an iterative solver, so a proximal gradients kind of approach. The solution is not unique. In L2 regularization, the WJs, the parameter values tend not to be actually equal to zero. With L1 regularization, they do tend to be zero. With L2 regularization, you can learn with a linear number of irrelevant features. And a result by Andrew Ng basically shows that you can learn with an exponential number of irrelevant features if you do L1 regularization. Okay. What is important is that you recognize that L1 regularization can be used to do simultaneous regularization and model learning, basically. But don't confuse L1 loss with L1 regularization. So L1 loss is the robust loss, which penalizes residuals not quadratically, but linearly. Okay. So L1 loss is robust to outlier data points. L1 regularization is what we just talked about, is robust to irrelevant features. Okay, so you can use that instead of doing search and score. And of course, you can actually put these two together, right? So you can be robust, so you can have a robust regressor, which uses an L1 loss, and you can also L1 regularize the weights or the parameters of such a model to do simultaneous model selection and regularization. An obvious question is, can we sort of, Huberize this regularization term? And the answer is sort of in between. The Huber regularizer is still robust to irrelevant features, but because it's actually quadratic here, it doesn't actually do model selection in the way you would want it to, because it has the diminishing returns problem that the squared loss does near zero. Okay, so you can't just replace this with a Huber loss and you make everything smooth, because you won't get weights that actually equal zero. Okay, cool. So what are the different kinds of regularization that we've talked about? We have L0 regularization, and basically that's all the canonical classical approaches that we named, but basically said penalize with some strength lambda the number of non-zero parameters in the model. Done. We talked about L2 regularization. We didn't use its classical name, but if you did a Google search for ridge regression, what you're going to see is you're going to see linear regression with an L2 norm squared, and then L2 norm of W as well. That's ridge regression. You can think about this as basically actually making a little ridge in parameter space where W's near zero are more likely. And then we just talked about lasso, which is L1 regularization, where we replace the 2 norm with a 1 norm. And this decreases overfitting in the standard way that regularization does, and actually does feature selection as well. And there exist iterative solvers for this, which are very, very fast and work with very large data sets and very large parameter spaces.
Can you combine L1 and L2 regularization?
Oh, amazing. Great. So that's actually really the only thing that I want to say on this slide, because again, we have a lot to cover. So it's worth noting, I will say this, L1 regularization isn't quite as sparse as L2 regularization. It tends to give rise to a few false positives. In other words, it over selects features. and it's only fast in one line in terms of implementation with specialized solvers. Combining L1 and L2 regularization is sparse, fast, and unique, and it's called elastic net. So you can do that. And combining actually the zero norm and L2 does not give rise to a unique solution. Okay, so last time we did radial basis functions, and now we just covered L1 regularization, which basically allows you to do simultaneous regularization and feature selection, and is robust to having lots and lots of irrelevant features. So we have a method now to sort of deal with the fact that we have lots and lots and lots of features, and we want to basically zero out a bunch of them. And now today, what we're going to do is regression for classification. Cool. Now I'll take questions while I'm switching slide decks. Okay, so last time, just now. Yep. Is there a reason we use the square root of the L2 norm but not the square of the L1 norm? Basically, so that when we do when we solve the normal equations, things work out. That's basically it. Doesn't really matter. Just algebraic niceness when you're solving that. Okay, cool. So we just talked about lasso, right? We don't have to do that again. It's convex and fast. Solution is not unique. Prone to false positives. Equivalently, we talked about ensembling before, so we can also ensemble for feature selection, right? And you usually do this to reduce false positives or reduce false negatives. We're not going to talk about that at all, right? In the case of L1 regularization, we want to reduce false positives, right? Cool. Unlike L0 regularization, the non-zero parameters are still shrunk. That's fine. The irrelevant variables can be included. Yeah, okay, whatever. It's the same thing, right? L1 regularization can produce false positives. So irrelevant variables can be included before the relevant parameters reach their best value. So how can we use ensembling methods to reduce this kind of false positive problem? Pretty straightforward. We're going to do the same thing we did before. We're going to generate bootstrap samples of the training data, and then we're just going to take the intersection of the features selected from all of the bootstrap sampled feature selection approaches. So here we're going to switch just a little bit to say, actually, let's L1 feature selection is one way to do it, but you could also do search and score. But let's, in our heads, think L1 regularization for feature selection. What we can do is take our original training data, generate in bootstrap samples, run our feature selection algorithm approach on each sample. That's going to give rise to relevant features, whatever those happen to be, for each of the bootstrap samples. And then actually one way to identify what we think are the, the relevant or whatever features is to take the intersection of all of the features that were determined to be relevant from all of the bootstrap samples and feature selection algorithms run on those. So an algorithm called Bow lasso is bootstrapping plus L1 regularization. It reduces false positives. And under certain weak conditions, it recovers the correct variables where correct is could that make false negatives now? Yes. This is all a little bit too squishy for my liking, but it's important that you know what these things are because you're going to end up needing to use these kinds of techniques. We don't know what's relevant. We don't know what's correct. Wouldn't intersection get rid of a lot of features? Not necessarily, right? So here it does. But you would expect if there are actually, if the true model family is in your in the support of the features in your basis, then you would expect that those true features would be stable across all bootstrap samples. And the intersection should recover those. Yeah, when might we need to handle exponentially scaling feature counts? Yeah, So we're going to get to that in just a little bit when we talk about how to actually build features for emails. So, basically anything, but one classic example, this is a good question, Dominic, is when you build bag of words representations for text documents, right? If you think about bigrams, unigrams, bigrams, trigrams, fourgrams, so on and so forth, and you count the occurrence of such features in documents, then you basically have an exponentially large feature space. Indeed, so for online stores, also like, the number of shopping baskets you can possibly have, like the fact that you bought all of these things is, is an exponentially large, the unique basket types are basically, there's an exponential number of them. So yeah, these are both good examples. Okay, cool. Other questions? I know I'm talking at full native English speaker speed, and I apologize for that, but we got to go quick today. Okay, let's go back to our email thread, no pun intended. So how can we automatically identify important emails? We're going to switch between important emails and spam emails, but let's think about important emails for the time being. This is a binary classification problem, important versus not important. You can approximately get the labels from user interactions. Basically, did you take some action? Did you reply to it? Did you, read it for a long time or something like that? We're going to have a high dimensional feature space here. This is going to be this, bag of n-grams kind of model, and we'll talk about that later. It might come as a surprise that actually Google uses regression for this binary classification problem, right? That's kind of crazy, right? How are they doing that, right? So put your thinking cap on, in particular Payman, who's going to stand in for everyone. Can we apply linear regression models for binary classification? Yes or no?
Yeah.
Yeah, okay, good. Are they going to work well?
Not necessarily.
Perfect answers, great, lovely. Okay, so everybody, yeah. Yes, because Google doesn't, yeah, right. Okay, first step to using regression for classification. First thing, we take our class labels, whatever they happen to be, right? Important or not important, or spam or not spam, or whatever. And we assign them numerical values. Typically, we'll use +1, -1. It works out in the math later that we're going to use +1, -1. Okay, so the point is we're going to actually numerically encode the labels, right? So if we have numerical outputs, then we can just fit a linear regression model. There's nothing, here's our weight vector, here are our features, whatever they happen to be, and here are our, forget the hat here, there's our output, right? And we've just encoded it like this, so we have numerical values, great, done, right? And it's pretty clear that what will happen is a linear regression model is going to try to make W transpose Xi close to +1, for important emails, and close to -1 for not important emails, right? There is an issue, and this is where this is kind of a fun explanation that we go through here, but it should ring true as we go through, right? Unfortunately, obviously, a linear model gives real numbered outputs, right? It's 0.9, -1.1, so on and so forth. And to predict, what we want to do is actually just see whether or not W transpose Xi is either closer to +1 or closer to -1, okay? So if W transpose Xi it lives on the real line, right? Just to be clear, and we have +1, -1, and this is W transpose Xi, okay? Which ones are closer to +1? Which values of W transpose Xi are closer to +1? Payman.
Sorry, what was the question?
Which values of W transpose Xi are, there we go. Nico's got it, he's paying attention. Dayu's got it, positive numbers, Ramon's, which I said correctly, he's got it too. All right, this is good, okay? So great, everything greater than 0 is closer to +1. Everything smaller than 0 is closer to -1, okay? So, but okay? Our loss, and I just want to sort of stick it in your head, right? Our loss is, and this is what we're going to dance around to sort of get to, right? We need some sort of loss function that we compute for output yi and transformed input w transpose xi, right? What we've talked about so far is yi minus w transpose xi squared. Okay, that's our loss so far, right? So what we want though is some loss function that actually is a little bit better for classification. And you'll see what's going on later. And just to think about it, we're going to eventually do something like this, just to foreshadow. We're going to put a sign in there, which is going to remove a bunch of problems. And we're going to get rid of this squared loss function because that squared loss function does weird things in regression. But anyway, for now, right, even if W transpose Xi is minus 100, we're going to predict minus 1 because minus 100 is closer to minus 1 than it is to plus 1, okay? So we're going to write this, and we're going to kind of, sign is going to be here and not be here in the lecture slides, but just keep in mind that we're going to often be plotting W transpose Xi as a continuous function, but you should be thinking about the prediction that we make as being the sign of that quantity, right? So anything on the right-hand side, anything positive should be a +1, anything on the negative side should be labeled -1. And this will become clear as we look at plots. In particular, we're going to look at xi right now, okay? So what's going to happen here? So this is the raw feature value xi. Here is our output. There are only +1 and -1 values in our training data. These are the important emails. They are labeled +1, so they all have exactly the same +1 value of important. And these are our not important emails. They all have the same -1 value, okay? All right. Great. What we'd like to learn somehow is a linear regression model, or if we did linear regression, that's what I should say. If we do linear regression, what we'd like is to somehow magically arrive, and sometimes it actually happens even with a squared error, particularly if you have nicely linearly separable data. You would like to have a linear regression model which produces an output value y hat I given an input value. Basically, this is the model, and we learn a W that does this, right? So you have to say, okay, where is W positive? Where is this positive? Well, it's everything to the left of this. And where is it negative? Everything to the right of that. Okay, so in the closeness that we just talked about, these are all going to be labeled. Any input that's in this range is going to be labeled -1, and any input that's in this range is going to be labeled +1 or important, right? So there's a decision boundary at W transpose Xi equals 0. Cool, okay? Our prediction function, right, is the sign after that, right? So this is yeah. So we can interpret this W transpose thing as basically a hyperplane separating our training data into two sets, right? There's a set where W transpose Xi is greater than 0 over here, and a set where W transpose Xi is less than 0 over there. Okay. Straightforward so far. Okay. Cool. All right. Now we are used to thinking about decision boundaries in some two-dimensional feature space x1, x2. We've got decision trees. We had axis-aligned splits. That was our decision tree boundary. In k-nearest neighbors, we had a non-parametric regressor where the decision boundary basically is a function of some number of nearest neighbors. In linear classifiers, basically the classification boundary is a hyperplane, okay? And here in this thing, you should think about the hyperplane is actually coming out of the screen, and the dividing line being where W transpose Xi equals 0, okay? fine. The other thing that you should think is that this hyperplane separating thing only looks like a plane, is planar only in the whatever basis you use, but that extended basis Z, a hyperplane, and that might be a much more complex surface in the original feature space, just as before. Okay. Cool. So the question is really, we're getting close. So what loss should we use? So should we use least squares for classification, right? And this is what we're going to think about right now. Should we use the squared loss in a classification setting? Does it make sense, right? So if we consider training by minimizing the squared error with y's that are +1 or -1, then we can think about what happens when we make certain predictions, right? And the label is a certain way, right? So if we make a prediction that has the correct sign, that got the right sign, but the wrong numerical value, but it's close, the error will be small, right? If we predict the wrong sign, i.e. it's far away from the true numerical value of the class, right, the error will be larger. But something funny happens with the L2 loss, which you're very familiar with, is that if we make up a prediction that has a very large large value but correct sign, the error is very, very large. But this shouldn't be the case, right? So we can't just use the 2 norm squared, because we're sort of, the loss function that we're using, this loss function, right, it's going to penalize us for being right, too right. That's not good. So basically, yeah, we'll see, right? So, you know, that's what it says here. It's like I've done this before. Least square is penalized for being too right. 100 has the right sign here, +100, so the error should not be large. So what's going on, right? So if you just take least squares and apply it to try to solve a classification problem, right? What we would like is that we have not spam, or I guess this is important and not important, or whichever it was, doesn't really matter. The linear regression model that we would like to have be basically a perfect classifier, right? When you apply the sign link function to its output, right? It looks like this green line, right? So you should understand why this green line achieves 0 training error, right? If you have this line, right, the sign of this is positive, the sign of this is negative, so everything in this region gets the correct label, and everything in this region gets the correct label. What we would actually get if we trained using the least squares loss here is this orange line. And why? It's because the squared error of the green line is large. In particular, if you think about like the residual for a data point like this, it's just going to go like crazy, right? So the orange line is going to have much smaller residual errors for the entire training data set than the green line is. So this is all very long-winded way and maybe slightly confusing way of saying we should not train linear models for classification using the squared error. Okay, because it's going to do goofy things. It penalizes being right too much, very badly, right? And in fact, basically in general, it's going to produce odd fits because of that. So it's going to, like the classification error of this orange line might not be too bad, but it's much worse than the green line. And we can't get the green line with a squared error loss, okay?
Can we just cap the prediction?
Can we just cap the prediction? Yeah, yes and no. So I see the sigmoid function is showing up here, and that'll be in the next lecture when we talk about the logistic sigmoid. But just capping it is complicated, and hopefully I'll be able to explain why in just a second. So one thing that we might like to do is just minimize directly the number of classification errors. And this is called the 0-1 loss function. Right? You either get the classification wrong or right. You get, zero error. Your loss function is 0 for all, evaluates to 0 for all of the sign that you match to the true labels, and 1 for all of the signs that mismatch. Okay. And we can write this using the L0 norm, right? So basically any mismatching signs are going to show up as a non-zero entry, and we want to minimize the number of non-zero entries in this vector, right? Okay. And of course, because we're talking about classification, we can actually talk about equality between y hat I and I, right? That's a sensible thing to do, right? We know we're restricting both y hat I because of the sign and yi to be just +1 or -1, okay? Now, it's worth mentioning, just for the fun of it, that there is a special case which is actually linearly separable data, right? So the classes can actually be separated by hyperplane, so a perfect linear classifier exists. In this case, a very old algorithm, which we mentioned basically for historical purposes and don't prove at all how it works or why it works, we just hint at it just a little bit, so these kinds of linearly separable data problems can be solved via the Perceptron algorithm. And it's one of the very first learning algorithms, like it's quite old, even older than me. This algorithm searches for a model parameter, a linear model parameter, such that the signs match, i.e. basically it classifies the data perfectly, as we just discussed, right? So the Perceptron algorithm works like this. You start with a 0 weight vector, and you go through all the examples in any order until you make a mistake predicting yi. And when you do, you update the parameter, your parameter vector, by adding in yi times xi, okay? Keep going through examples so you make no errors on the training data, okay? If a perfect classifier exists, I'm just gonna say this, we don't prove it, it's actually a little bit difficult to prove. So we'll just say it. If a perfect classifier exists, the algorithm finds one in a finite number of steps. Of course, we're assuming a priori that the data is linearly separable, which is a very, very unrealistic thing to assume before you even start trying to do some sort of fitting of a model. But it's worth understanding that if linearly separable data, if the data is linearly separable, then the Perceptron algorithm will find in a finite number of steps a perfect classifier, i.e. a weight vector that actually perfectly classifies the data. The intuition of what's going on is if the current weight vector gets a particular example wrong, right? So in other words, W transpose Xi is less than 0. One example would be if the W transpose Xi is less than 0, but Yi is actually +1, it's positive. The update rule would say, okay, make W at the next iterative of the algorithm T+1, well, make that equal to W transpose plus Xi. That's exactly what this and this would do, right? So yi is 1, so we're going to add a bit of xi to w at time step t, right? And if you work this out, this is the same. This is the weight at the previous time step times xi, dot product with xi plus some positive number, right? So basically, by updating in this particular way, in this particular circumstance, you're adding a positive, like the new value of W T+1 transpose Xi is going to be more positive than W T transpose Xi. So this will be more positive than this by this amount, okay? And by making it more positive, this violation will be less likely to occur, right? Cool. So it's the old prediction plus some positive number. And obviously, if y equals -1, you would subtract the squared norm. In fact, they built machines for the Perceptron algorithm way back in the day. The Mark I Perceptron machine basically took some inputs x, did some feature transformations internally, made an output, and had potentiometers that actually represented the weights of the network. So this has been around for quite a long time, okay? For image classification, actually, which is kind of cool. So let's think about why we want the 0-1 loss, and then we're going to go quickly through the derivation of a bunch of interesting stuff. So we're going to plot something a little bit complicated to think about, but bear with me, it's not that bad. This is the error or loss for predicting on a single example, W transpose Xi, when the true label Yi is -1. So, here's a point on this W transpose Xi axis, right? You can think of this as either a function of W transpose Xi, you can think of this as a function of W with Xi fixed. There's a bunch of ways of thinking about it. But you really just think about it as W transpose Xi, right? Whatever this value is and whatever you're varying, whether it's the value of Xi or W, is really W that we're going to vary, right? Having W transpose Xi here is bad, right? If the actual value of Yi equals -1 is over here, we really want the sign to be negative, right? So having W transpose Xi over on the right-hand side is bad. We should penalize this. There should be a loss for this, right? If W transpose Xi, we're going to move W around eventually, right? But for a particular W and a particular Xi, right? You should not get penalized for putting W transpose Xi over here. If the sign of W transpose Xi is negative, you're fine, right? There should be no penalty. So the loss, right? Again, just thinking about this as some arbitrary quantity that we're plotting on the horizontal axis, the loss that we're adding up when we're training our linear regression, our linear classification model, if we were to use the squared 2 norm, is this, right? We're going to penalize W's, right? That if that produce a response different than Yi by a quadratic amount in this direction. That's good, right? So these should have large error because they're wrong. But over here, we're going to penalize for being too right as well, okay? That's bad. We don't want to do that, okay? So just to be clear, we're plotting the loss versus the predicted W transpose Xi. So that eventually we're going to be moving W around. That's what we're going to do. But you can think of this as like just, the X axis value. That's it, the dot product value, right? This is loss space, which is different parameter space and data space. And we're plotting an individual loss for a particular training example. And you can think about like moving W somehow. That's kind of what you can think about for how to think about the loss here, right? In the figure in the figure that we just showed, and we're going to show again, the label is Y equals -1, so the loss is centered at -1, right? And it will be centered at +1 when the label is +1. And the objective in least squares regression is the sum of n of these losses, as always. Okay, so the same plot is here, right? Yeah. So the loss, right? The loss will be minimal if W transpose Xi is equal to Yi. That's clear, right? And if it's not, it's going to be large in this direction and large in this direction, okay? Under the square 2 norm. You could think about doing something like making this the absolute error. So in other words, doing L1 robust regression, kind of, right? So the absolute error reduces, but does not fix the issue. So we're still getting penalized over here as we should. Okay, there's a little penalty here. That's not necessarily actually so bad. We can talk about that. We'll try to make some intuition about that later. But you're still getting penalized over here linearly rather than quadratically for being too right. Okay, great. What we want is the 0-1 loss. That's ideally what we would want, because basically over any W transpose Xi that's positive in this particular case, we should get doesn't matter what the value is, we should get a constant error of 1. It's a misclassification if it's over here, right? And over here, no matter what, if W transpose Xi is negative, we should get no penalty whatsoever because it's not we correctly classify it, okay? There's some unfortunate issues with the 0-1 loss. The biggest one, and this is related to the sigmoid problem as well, is that over here, there is no gradient signal. Right? If you think about trying to minimize this loss with respect to W, so you're going to mess around with W in order to try to make this loss as small as possible, right? There's no gradient signal at all, right? None over here either, okay? It's also not convex. There's a problem there, right? So the 0, 1 loss is non-convex in W. You know, there is an algorithm. That's why we've talked about the perceptron algorithm. If a perfect classifier exists, if the data is linearly separable, otherwise finding the W that minimizes this 0, 1 loss is a very hard problem. Gradient is 0 everywhere. We don't even know which way to go, so we can't do gradient type methods. And this is not the same kind of problem we had with using the squared loss. We can minimize the squared error, but it might give a bad model for classification. The 0, 1 loss we can't minimize. It would give a great model for classification, right? And what this has done is basically this is our way of motivating convex approximations to the 0, 1 loss that give rise to modern linear classification models, right? Okay, so let's talk about a degenerate convex approximation to the 0, 1 loss, right? So imagine the following. This has been pretty well established at this point. So if y1 is +1, we get the label right if the sign of W transpose xi is positive, right? If yi is -1, we get a label right if the sign of W transpose xi is less than 0, or equivalently minus W transpose xi is greater than 0. Same thing, right? These are equivalent, right? And this is the linear classification trick that everybody uses, right? So classifying I correctly, right, is equivalent to having yi, the numerical value +1 or -1, times W transpose xi being positive. Okay, fine. So one possible convex approximation to the 0, 1 loss is to minimize how much this constraint is violated. You know, if you if W transpose xi is greater than 0, you get an error of 0. Otherwise, you get an error of minus yi W transpose xi. And if you stare at this for long enough, you'll see that this thing is going to be a positive quantity if the sign of yi and W transpose xi don't match. Okay, so the error, the loss that we want to operate with is the maximum of 0 and minus yi W transpose xi, which will be a positive quantity if W transpose xi and yi don't match signs. Okay, fine. This happens to be convex. You can use the rules that we have to verify this, right? And this is what's called the Hinge loss. Okay, so we have the quadratic loss that we talked about. We want the 0, 1 loss, and the function that we just wrote down is the Hinge loss convex approximation to the 0, 1 loss. So it penalizes less here and more here, but correctly, it does not penalize over here. Okay, fine. Fine. So this is basically just keep it in your head that we're replacing the squared 2 norm, right? We're replacing the squared thing with some more sensible loss function, right? So the convex approximation of the error for one example looks like this. We can train by minimizing the sum over all examples. Unfortunately, if you look at this, there's an easy way to cheat. You just set this W equal to 0, then this whole thing evaluates to 0.
Explain why doesn't the 0, 1
We'll come back to that. Yeah, we can come back to that. But I mean, it's pretty. So think about. So I said basically you can think about moving along in this direction by varying W, right? So the gradient of this particular loss function at this particular point clearly as a function of W. If you think about that as X is being fixed and W is the only variable that's moving, the gradient here is 0, right? It's flat, right? And same thing over here. The only place where there's a gradient is right here, and then it's infinite. So it's kind of even worse. Hopefully that that's enough to get you going for now. Okay, so we can cheat with this particular degenerate convex approximation, right? The hinge loss. Sorry, I shouldn't say that. Hinge loss, but we're going to talk about a degenerate approximation here, right? So the degenerate thing is if this W is equal to 0, right? Then it's uninteresting. To minimize this loss, we just set all the weights of the model to 0 and we're done, right? That's the lowest possible thing. There are two standard fixes, the hinge loss, which is not degenerate, excuse me, and the logistic loss. And we're going to talk about the hinge loss, and that'll be it for today. So the hinge loss says, look, if we classify examples I correctly, if that yi w transpose xi is greater than 0, and our convex approximation is the amount this inequality is violated. So why don't we just actually make it so that we want to make things more right. This will make sense in just a second. So we're consider replacing this 0 with a 1, right? The 1 is arbitrary. We can make the norm bigger or smaller to use any positive constant, just got to be non-zero. The violation of this constraint now is given by max 0, 1 minus this, okay? And this is called the hinge loss, okay? It's convex, and it's not degenerate, because if you set W equal to 0, then you have a non-zero loss, which you might be able to improve, okay? So what is if you just plot the hinge loss, if you look at what this function is, if you stick in W transpose x equals 0, then this is 1. So you're going to see that it's 1 here. You can verify that it's 0 at y equals minus 1. Cool. So basically, this is if you just plot what we just described, what we just wrote, that's the hinge loss. Okay? This is versus the degenerate loss that we had before. It's convex, close to the 0, 1 loss, right? Notably, it does penalize you for making correct predictions that are too small in value, right? So you really want to make all of the signs of the negative examples greater than -1. That's really important, right? That's this hinge loss, the margin, the whatever. There's lots of different words for it, right? It does penalize incorrect things linearly. That's fine, right? So big positive values are also not good. But you should note that this is happening. So it's really going to try to push negative examples like this. Same thing for positive examples. If you flip this, if you just look at what the loss for predicting W transpose xi is when the true label is +1, you get this plot. And again, there's this little extra penalty that encourages the regression model, the linear classification model to learn W's that actually separate the positive and negative examples by at least the margin, whatever that happens to be. Okay, convex, always above 0, 1 loss, fine. So it's an upper bound on the loss. So the hinge loss for all 10 or for all n training examples would be given by just summing up the hinge loss over all training examples. Again, this replaces the square loss that we would have had, right? So it's still a linear model, right? But instead of the squared loss, we can use something like this, right? Convex, right? It's upper bound on the 0, 1 loss. So if the hinge loss is, for instance, 18.3, then the number of training errors is at most 18. That's cool. So it doesn't minimize the classification error exactly, right? But it indirectly tries to minimize it, right? So it's a proxy, it's a bound. It's a good bound, and if you attempt to minimize this when there is actually in the same conditions that the perceptron finds a perfect linear classifier, this too will learn a perfect linear classifier. And probably the most beautiful conclusion to one of these explanation trajectories in this class is the way we describe what a support vector machine is, which can be described much more brutally mathematically. Here, we just say that a support vector machine is a linear model for classification that uses the hinge loss that we just described, plus L2 parameter weight regularization. learning or estimating a W for this support vector machine is not super straightforward. It's a classic final exam question to make you actually implement this. There exist specialized optimization algorithms for this problem. There's tons of them. This was a very important class of machine learning algorithms for a very long time, still very widely used. And you can think about support vector machines as maximizing the margin, which basically has to do with the slack that we just talked about, or this extra one here. Okay. So sorry I ran a little bit late, actually quite a bit late today. So in summary, we did a couple of things. We did feature selection by L1 today. We did ensemble feature selection, which can be used to reduce false positives in feature selection. We did binary classification using regression. Now, where we encode the outputs numerically, we use sign of the linear model as our predictor. And this gives rise to a linear classifier, basically in the form of a hyperplane splitting the space in half in whatever basis you're in. Least squares doesn't really work for classification because it's weird and penalizes being right by too much, by a lot. And we said that there exists a Perceptron algorithm that finds a perfect classifier if your data is linearly separable. And we introduced the Hinge loss as a convex upper bound on the 0-1 loss, which basically replaces the squares part of least squares with a different loss function. And that Hinge loss is what is used in support vector machines in combination with L2 regularization. Of course, we'd like to use the 0-1 loss, but we can't. It's not smooth, and it's non-convex, and there's no gradient to follow anyway. So, cool. Why are they called support vector machines? We're going to basically avoid that in this class, but basically there's you can express the form of the hyperplane in terms of a linear combination of so if you have x's and O's like so, and there is a hyperplane that separates them. We'll talk about this a little bit, I think, I don't remember. And you want to form basically the equation for the hyperplane. You can derive support vector machines in such a way that you see that you only need basically some small number of nearby points to define the hyperplane, and all of the other points you can just ignore. These points that the support vector machine identifies are called the support vectors, and that's what the support vector machine is named for. Are support vector machines with elastic net regularization a thing? Ooh, probably. I don't remember off the top of my head. That is a classic machine learning research question. What if we did elastic net regularization with support vector machines? What would happen? And you could probably Google for that and get the answer faster than I can possibly remember it, because there's 8 billion of these kinds of things out there. Do you remember, Payman? Do you know? I don't know. I didn't catch up with the part that what penalty of hinge loss will affect W. Could you explain that again? I'm not sure, Shuyan, that I understand the questions, and you don't have to call me sir. You can just call me Frank. I appreciate the formality and respect. Penalty of the hinge loss will affect W. Could you explain that again? what's going on here is a little bit difficult. Maybe what's going on here is a little difficult to really make super clear, and honestly, you just have to think about it for quite a while, right? So ultimately, in the outer loop of everything, we're trying to learn some W, right? And what we're plotting here is a loss that we're minimizing at some particular time, right? And what we're saying is that for an instance xi, yi, where yi equals 1, and some W transpose, right? We're just trying to look at what happens. We don't. I'm saying we don't know what this xi is, right? But if the xi is such that when you compute this, it lands here, right? There's going to be a loss that the overall optimization algorithm is going to try to minimize, right? And in fact, it's going to be this loss right here, right? Because W transpose xi has the wrong sign if this particular W xi and this particular W at some point in the optimization produce a positive value, right? So the question is, how do we penalize the difference between W transpose xi and yi, right? And for
I think he's particularly asking about between -1 and 1. Why we shifted over, like.
Oh, I've got an okay haha from, so I think maybe what I was rattling on about actually made sense. Great. So I'm gonna go with okay haha. That means I think it's clear enough. Good. You're very welcome. Yeah. Any other questions? Midterm questions? No, it's past time. Everybody's probably already in another lecture. There's only 19 people, so unlikely. Thank you very much.